For several weeks, the object known as Atlas behaved exactly as astronomers expected. Its projected path was stable, its motion consistent with natural celestial dynamics, and every new measurement confirmed the same conclusion. It would pass Earth at a safe distance without posing any threat. All global tracking systems agreed. Nothing indicated that the object was anything more than another interstellar visitor moving through our solar system according to predictable physical laws. That assessment changed abruptly. Late last night, observatories on multiple continents detected a deviation in Atlas's trajectory. At first, the shift appeared to be a minor discrepancy, something that could be attributed to measurement noise, instrument calibration, or a brief outgassing event. But within minutes, new data arrived, and the revised orbital models began to converge on the same conclusion. The deviation was not minor, it was not accidental, and it was not consistent with any natural force acting on the object. Atlas had altered its course. The change was sharp, controlled, and executed with a level of precision no comet or asteroid has ever demonstrated. Its velocity increased, its vector tightened, and its projected path began to curve unmistakably toward Earth. The numbers left no room for interpretation. A massive object, hundreds of billions of tons in estimated mass, had performed what can only be described as a targeted maneuver, one that required an enormous energy expenditure and an understanding of navigation impossible for any naturally occurring body. As this information reached research centers around the world, analysts and mission planners came to the same conclusion independently of one another. The event was intentional, and whatever caused it was operating far beyond the technological capabilities of present-day humanity. With each new update, the situation grew more complex. Atlas was no longer simply passing through the solar system. It was approaching. The time frame for its closest pass shrank. The distance at which it would cross Earth's orbit decreased, and the margin for error, a margin that once spanned millions of kilometers, collapsed to a number so small that global agencies began quietly activating emergency evaluation protocols. What unsettled researchers most was not the trajectory change itself, but the implications behind it. A course correction of such magnitude implies a decision. A decision implies control. And control requires a level of engineering, energy generation, and physical understanding that humanity does not yet possess. For the first time in recorded history, we were forced to consider the possibility that an interstellar object had performed a maneuver with a defined objective. And that objective appeared to be us. The question that immediately surfaced across scientific and strategic communities was simple but unprecedented. If Atlas continues on its current path, what, if anything, can humanity do in response? Our largest rockets, our most advanced propulsion systems, and the full combined output of our global space infrastructure are insignificant compared to the mass and momentum of an object traveling at interplanetary velocities. Even our theoretical planetary defense strategies, including nuclear deflection, are designed for natural asteroids, not for a target capable of adjusting its own trajectory with unknown precision and unknown power. Simply put, humanity does not currently possess a system capable of intercepting, redirecting, or halting an object like Atlas. This realization triggered a wave of silent urgency behind the scenes. teams began assessing every possible response: scientific, diplomatic, defensive. Yet each option returned the same problem. Without understanding the nature of the maneuver or the mechanism that enabled it, predicting what Atlas might do next became nearly impossible. If the course alteration was a signal, we had no method to interpret it. If it was a threat, we had no method to counter it. And if it was something else entirely, then the margin for strategic error was dangerously high. For now, all we know is this: a massive interstellar object, previously considered harmless, has executed a powered trajectory adjustment that directs it toward Earth. The event has already rewritten several branches of astrophysics. It has forced international organizations to reconsider long-standing assumptions about cosmic threats. And it has raised a question humanity has never had to answer at this level of seriousness. What response exists when the universe demonstrates the ability to reach us with intention? This is where the story begins, not with panic, not with speculation, but with a single fact that cannot be ignored. An object that should have been bound by natural forces alone has performed an action that defies every natural explanation. And whatever the purpose behind that action may be, the consequences of it will shape the future of our species in ways we are only beginning to understand. As additional observatories synchronize their data, a clearer picture of Atlas's maneuver began to emerge. The trajectory alteration was not a gradual drift, but a rapid, high-energy burn, sustained long enough to generate measurable thermal and electromagnetic signatures. Infrared telescopes detected a sudden rise in surface temperature, far beyond what any natural sublimation or outgassing event could produce. The emissions were localized, coherent, and consistent with directed propulsion, rather than anything chaotic or naturally occurring. This was the first definitive indication that Atlas possessed an internal system capable of generating and expelling energy at a scale unprecedented in known physics. The propulsion vector matched the change in course with mathematical precision. There was no deviation, no scatter, no noise pattern typical of natural cometary activity. The maneuver was executed with purpose and stability, characteristic of controlled thrust. Following these observations, global monitoring networks expanded their focus from positional tracking to full spectrum analysis. Radio telescopes detected bursts of structured electromagnetic activity that coincided with the propulsion event. Although the patterns have not yet been decoded, the signals displayed non-random modulation patterns that repeatedly match the statistical signatures of engineered transmissions. Scientists are currently divided on whether the emissions were an intentional broadcast, a byproduct of the propulsion mechanism, or something else entirely. But regardless of their origin, the conclusion was unavoidable. The object possesses systems of artificial complexity. With each confirmation, international agencies were forced to abandon the last remaining natural explanations. The probability that Atlas is of artificial origin, whether a probe, a vessel, or an automated intelligence, rose from speculation to near certainty. The implications reached far beyond scientific curiosity. If the object is controlled by an intelligence, then its trajectory toward Earth cannot be dismissed as chance. It must be analyzed as a deliberate action with an underlying motive, one that remains unknown. Strategic analysts immediately began forming preliminary threat assessments, not because confrontation is possible at this stage, It is not, but because understanding intent is the only meaningful form of preparation available. The initial reviews highlighted a series of unresolved questions. If Atlas is approaching Earth intentionally, what is the scale of its mission? Is it observing us, responding to us, or seeking contact? Or is its purpose entirely unrelated to humanity, with its trajectory toward Earth merely a waypoint on a broader path? The concerning element is that none of the available scenarios reduce the significance of the object's maneuver. Whether Atlas intends communication, study, intervention, or something more complex, the simple fact that it can adjust its course demonstrates an operational capability that far exceeds anything humanity has developed. Even our most advanced spacecraft can barely perform controlled maneuvers at interstellar distances. Atlas executed one that changed the dynamics of the inner solar system. Meanwhile, the general public remains unaware of the full scope of the event. Governments are delaying disclosure, hoping to gather more data before releasing information that would likely trigger global uncertainty. Emergency committees are being formed discreetly. Research institutions have shifted into continuous monitoring without announcing the reason for the increased vigilance. And behind closed doors, discussions have begun about a possibility that was once considered purely theoretical. How can humanity respond to an approaching object that demonstrates intelligence? The difficulties are immense. Traditional planetary defense models are entirely ineffective against a target capable of active navigation. Systems designed to intercept asteroids depend on the predictability of natural trajectories. If Atlas can adjust its path at will, any defensive attempt would be countered before it begins. Even coordinated nuclear deflection strategies, which are considered the last line of planetary defense, are rendered obsolete. A nuclear blast relies on imparting enough force to alter a fixed trajectory, but against a maneuver-capable object, the effect would be temporary at best. Furthermore, the energy signature detected during Atlas's course correction suggests that its propulsion power dwarfs any force humanity could realistically deploy. To match the object's maneuvering capability, even for a second, would require output comparable to the most advanced fusion systems, a technology we do not yet control. In practical terms, this means that humanity cannot redirect Atlas, cannot destroy it, and cannot outrun it. The only viable strategy is observation until more information becomes available. Yet observation alone is not a passive act. Every scrap of data thermal patterns, radio emissions, spectral analysis, gravimetric fluctuations is being collected and compared against models designed to identify technological origin. Teams specializing in artificial intelligence and signal analysis are attempting to determine whether the object's behavior follows patterns consistent with decision-making processes. Others are modeling hypothetical trajectories the object might adopt next to determine whether its current path will remain stable or continue tightening toward Earth. Parallel to these scientific efforts, discussions have begun about potential communication strategies. If Atlas is transmitting intentionally, then recognizing even a single pattern within its emissions could serve as the first step toward decoding a signal. But establishing communication carries risks. Making contact prematurely could reveal strategic information about humanity's capabilities or lack thereof. Remaining silent could be interpreted as avoidance. There is no precedent, no protocol, and no margin for error. For now, the global scientific community is focused on a single objective: determining whether the object's current trajectory will bring it into close proximity to Earth. Early projections indicate that if no further maneuvers occur, the approach distance will be significantly closer than previously expected. This alone would represent the most significant astronomical event in modern history. But the unknown variable remains whether additional course corrections will take place, further narrowing the gap. As each hour passes, new data is added to the models. With that data comes the same fundamental realization: the maneuver performed by Atlas was not simply a change in direction. It was an announcement, one expressed not through language, but through action. A statement that an intelligence with capabilities beyond our own has entered our region of space and is moving with deliberate intent. The significance of this cannot be overstated. For the first time, humanity is not studying a passive cosmic object. It is observing an active agent. And whether Atlas is approaching for reasons benign, neutral, or hostile, its presence forces humanity to confront a reality long considered distant and hypothetical: the possibility that we are no longer the sole architects of our future in this solar system. The next phase of analysis will determine whether Atlas continues accelerating, stabilizes its trajectory, or prepares for another maneuver. Each outcome carries its own set of implications, each one pointing toward a direction that will define the nature of humanity's response. For now, the world remains unaware, the data continues to accumulate, and the object continues to close the distance. The question remains unchanged. If Atlas is acting with intent, what purpose lies behind its decision to turn toward Earth? As tracking networks continue to refine their measurements, a new set of phenomena emerged that further complicated the assessment of Atlas's nature. During the final minutes of its trajectory change, multiple sensors recorded fluctuations across several electromagnetic bands. These fluctuations were brief but unmistakably structured. They did not resemble solar interference, background noise, or any known natural astrophysical process. Instead, they appeared synchronized with the object's acceleration, as though the propulsion system, or whatever mechanism generated the maneuver, also produced a series of emissions consistent with engineered control signals. Spectral analysis revealed narrowband peaks at specific repeating frequencies. Their spacing followed ratios not commonly found in natural plasma events or ionized gas interactions. While no decoding has been achieved, early examinations indicate that the emissions carry internal organization, suggesting a layered system capable of transmitting information or regulating onboard operations. For analysts, this raised the probability that the object is not merely capable of propulsion, but possesses integrated subsystems designed for coordination, navigation, and potentially communication. Parallel to electromagnetic observations, several deep space monitors detected localized increases in high-energy particle activity surrounding the object. These spikes were brief, lasting only seconds, but they aligned precisely with the start and end of the maneuver. Models attempting to replicate the readings using natural processes failed to produce the same results. The patterns more closely resemble controlled particle acceleration, similar in concept, though vastly greater in scale, to experimental drives proposed in theoretical propulsion research. The implication is that Atlas may utilize a method of thrust fundamentally different from chemical or ion-based systems, possibly involving directed particle beams, or controlled energy fields. With each passing hour, the event gained layers of complexity. By the time the sun rose over the first observing nations, scientific institutions had already issued classified briefs summarizing the findings. These briefs emphasized that the object's behavior met multiple criteria for artificial operation. Among the key points were sustained energy output inconsistent with natural bodies, mathematically precise trajectory alteration, structured emissions across multiple frequency bands, and thermal signatures matching engineered activity rather than passive reflection. The combined weight of these observations led to the formation of new advisory groups within several national agencies. These groups brought together astrophysicists, propulsion experts, communications engineers, and strategic analysts. Their purpose was not only to determine the nature of Atlas, but to outline potential scenarios for its continued approach. One of the initial tasks was establishing baseline categories for possible intent ranging from observational to mission-oriented, from neutral passage to deliberate engagement. Although no conclusions were reached, one consensus emerged. Any prediction based on human technological logic may be unreliable. If Atlas originates from a civilization significantly older or more advanced than humanity, its behavior might follow principles unavailable to current understanding. The comparison used internally was simple. Attempting to analyze an interstellar craft using present-day human models could be similar to applying medieval physics to a modern satellite. The gap in capability introduces an unavoidable margin of error. As this framework developed, attention shifted to the second major question raised by the maneuver. What, if anything, can humanity do in response? The practical answer remained unchanged. No existing system on Earth can alter, intercept, or neutralize an object with Atlas's demonstrated capabilities. The scale of its energy output places it beyond the reach of any defensive strategy. Even the most extreme proposals, including nuclear deflection, kinetic impact, or gravitational manipulation, offer no viable solution. An object capable of self-correcting its path can counter any attempt to redirect it, rendering traditional methods ineffective before they even begin. However, discussion did not end there. Analysts considered secondary layers of response, monitoring, communication, and preparation for possible contact. Monitoring is already underway, with every applicable system, orbital, ground-based, and deep space dedicated to continuous observation. Communication is more complex. While Atlas has produced emissions, their purpose remains unclear. Attempting to respond might risk exposing human limitations or technological signatures unintentionally. Conversely, remaining silent could be interpreted unpredictably, depending on the nature of the intelligence operating or programming the object. To address this, communication specialists have begun developing passive listening protocols, focusing on identifying patterns within the object's emissions. If a clear repeated structure appears that suggests intentional outreach, humanity may attempt a measured reply. But such a step requires extreme caution. A premature communication attempt made without understanding the context or meaning of the signals could introduce unnecessary risk. The third component, preparation for potential contact, is the most uncertain. Historical discussions on first contact scenarios largely exist in academic or theoretical contexts. In practical terms, humanity has no unified protocol. Each nation holds its own position. Each institution follows its own interpretation. And each discipline, scientific, military, philosophical, approaches the situation with different priorities. The arrival of Atlas forces a shift from hypothetical planning to real-world necessity. If the object continues its current course, the approach distance is projected to fall within a range that guarantees direct observation from Earth-based instruments. In this scenario, the planet will witness the closest encounter with an interstellar object in recorded history. Depending on the object's actions during approach, this could either provide critical scientific insight or escalate concerns dramatically. Any further maneuver, no matter how minor, will be analysed in real time for indications of intent. Teams are currently modelling potential behaviours Atlas might exhibit during approach. These models are not predictions, but contingency frameworks designed to prepare responses to various outcomes. For example, if the object reduces speed, this could indicate an observational mission or preparation for controlled orbital insertion. If it accelerates, the purpose may involve transit or repositioning. If it emits additional signals, analysts will assess whether the patterns show repetition, sequencing, or information density consistent with communication. And if it performs another trajectory correction toward Earth, the situation enters a new and unprecedented stage. This is the point at which the scientific analysis transitions into strategic planning. Global security councils are evaluating secondary consequences. These include public reaction, economic disruption, and the necessity of emergency coordination. While no public announcement has been made, several nations have initiated quiet preparations for the possibility of global disclosure. The timing of such disclosure depends on whether Atlas performs additional maneuvers or maintains its projected path. For now, the object's behavior remains stable following the initial course correction. Instruments continue to monitor for changes, and every hour adds new data to the collective analysis. Yet the underlying reality remains unchanged. Atlas executed an intentional shift toward Earth, backed by a propulsion system that exceeds human capability. This places humanity in a position for which there is no precedent. For the first time, our species must evaluate the approach of a potentially artificial interstellar object whose objectives remain unknown. The situation demands caution, focus, and continuous observation. What happens next depends entirely on the object's subsequent actions, and until those actions reveal more, the world waits quietly, unknowingly, and on the threshold of a moment that may redefine the future of our civilization. In the hours following Atlas's maneuver, attention shifted to another emerging aspect of the event, its internal structure. Until now, the object was assumed to be similar to other interstellar visitors. Irregular in shape, composed of frozen volatiles, dust, and rock, with a surface shaped by micrometeorite impacts and thermal stress. However, as more advanced instruments focused their observations, inconsistencies appeared between expected natural formations and what was actually detected. Radar imaging returned surprisingly clean reflections, indicating surfaces that appeared smoother and more uniform than those typically found on cometary bodies. Some regions showed geometric angularity patterns difficult to reconcile with naturally formed topography. Several panels reviewing the data noted abrupt boundaries between reflective zones, raising questions about whether these areas represent structural components or engineered plating. While the resolution remains insufficient for definitive classification, the uniformity of these features continues to draw attention from structural analysts. Thermal mapping also revealed anomalies. Natural bodies absorb sunlight and radiate heat in patterns dictated by their material composition and rotational speed. Atlas, however, displayed temperature gradients inconsistent with rotation alone. Instead of warming uniformly under solar exposure, some sections maintained stable temperatures even as they moved into sunlight, suggesting either controlled thermal regulation or the presence of materials with extremely unusual heat absorption properties. Other regions exhibited rapid thermal fluctuations unrelated to surface lighting conditions, raising the possibility of internal processes or heat dissipation systems. These findings prompted a shift in the scientific approach. Instead of treating Atlas as a singular anomaly, analysts began comparing its behavior to hypothetical constructs proposed in research surrounding interstellar probes and autonomous craft. Many of these theoretical designs involve modular internal architecture, robust thermal management, and layered systems capable of withstanding extreme conditions during long-duration travel. Although none of the observed features provide conclusive proof, the cumulative evidence has pushed the probability of an artificial origin to its highest level since tracking began. Meanwhile, research groups specializing in orbital mechanics have continued refining their models. The initial maneuver, once considered an isolated event, now appears to be part of a larger trajectory pattern. Subtle deviations have been detected since the main correction, too small to classify as full maneuvers, but significant enough to suggest fine-tuning. These micro-adjustments may indicate that the object is maintaining a precise course relative to Earth's position, compensating for gravitational influences or ensuring a specific approach angle. The pattern resembles guided navigation rather than passive flight. With each improvement in data resolution, the strategic implications become more difficult to ignore. If Atlas is navigating with precision, then its current path is not the result of a random alignment, but the product of deliberate control. This possibility has driven governments to expedite internal reviews. The central issue is not only the origin of the object, but its projected proximity to Earth and the potential form that proximity may take. Analysts are evaluating the difference between a near pass, an orbital insertion, or a controlled deceleration, each outcome carrying drastically different consequences. If Atlas intends to maintain high velocity during approach, the encounter would be brief, allowing minimal interaction but offering significant observational opportunities. If it begins to decelerate, however, the implications change. Deceleration would indicate preparation for long-duration presence within the inner solar system, possibly including orbital stabilization or a direct approach vector toward Earth itself. At present, there is no evidence of velocity reduction, but the possibility remains under continuous evaluation. In parallel, intelligence agencies have begun assessing the potential impact of public disclosure. Should the object perform a second maneuver or reduce its approach distance further, withholding information may no longer be feasible. The concern is not simply public reaction, but global coordination. If nations attempt to respond independently, without a unified framework, the risk of miscommunication or escalation increases significantly. Efforts are now underway to establish channels for coordinated analysis, although political differences continue to delay full cooperation. One of the most pressing issues arises from the limitations of humanity's observational capability. Even with advanced telescopes and deep space monitoring systems, the resolution required to determine Atlas's exact composition remains beyond reach. Space agencies have proposed accelerated mission concepts involving rapid launch probes equipped with high-speed intercept trajectories, but development timelines present a major obstacle. Existing spacecraft cannot reach Atlas before its projected approach, and constructing new ones in time may not be possible unless extraordinary measures are taken. Nevertheless, several agencies have begun preliminary planning, focusing on repurposing available hardware or utilizing untested propulsion configurations to reduce transit time. These discussions remain internal, as the feasibility of such missions is uncertain. Even if a probe could be launched, the object's potential maneuverability raises concerns that it could evade interception or alter its path unpredictably. The lack of reliable data continues to limit operational planning. At this stage, humanity remains fundamentally unprepared. Every discipline involved, astronomy, physics, engineering, communications, strategy, faces gaps in knowledge too large to bridge without further information. As a result, the global focus has shifted to careful observation, rigorous measurement, and avoidance of premature conclusions. Scientists emphasize that the object's intent cannot be inferred from its behavior alone. While the maneuver was deliberate, it does not inherently imply hostility. It may represent reconnaissance, investigation, a navigational adjustment, or a purpose unrelated to Earth entirely. However, strategic planners proceed under a different set of assumptions. Their role is to prepare for the broadest range of possibilities, including those that present potential risk. From their perspective, the critical factor is not the object's motive but its capability. Regardless of intent, Atlas possesses technological and energetic capacity that surpasses anything humanity can counter. This alone places it in a category where uncertainty becomes a strategic vulnerability. The tension between scientific caution and strategic concern is now shaping how information is processed. Every new data point is evaluated through both lenses, the possibility that the object is benign and the possibility that it is not. Neither perspective holds dominance, and both are influencing the early stages of global response development. Meanwhile, the object continues its approach, closing the distance at predictable intervals. The next major update will rely on refined trajectory calculations expected within the coming days. If the new models indicate an even closer path than currently predicted, or if Atlas performs another navigation adjustment, several agencies will transition from analysis to early-stage contingency activation. For now, the situation remains stable but unresolved. Atlas travels silently through the inner solar system, exhibiting characteristics inconsistent with any known natural phenomenon. Its origin is unclear, its intentions unknown, and its capabilities far beyond existing human technology. All that is certain is that the maneuver it executed marked a turning point. Before that moment, Atlas was simply an object, a point of interest. After it, it became something else entirely, an active presence moving along a controlled path. And until further data reveals more, humanity stands at the threshold of a scenario with no precedent in its history, awaiting the next signal, the next maneuver, or the next indication of what this object truly represents. As international teams deepened their analysis, a significant development emerged from the departments responsible for high-resolution spectroscopy. For the first time since the trajectory correction, the light reflected from Atlas began to reveal unusual spectral signatures. Under normal conditions, interstellar bodies display predictable absorption lines corresponding to common ices, minerals, and carbon-based compounds. However, several of the new readings diverged sharply from those patterns. The lines were narrow, stable, and repeated across multiple scans, suggesting the presence of alloys or materials not commonly formed through natural cosmic processes. Some of these signatures aligned with theoretical constructs proposed in advanced materials, research substances engineered to withstand extreme stress, radiation, and thermal cycles far beyond the tolerances of naturally occurring minerals. These findings added weight to the growing likelihood that Atlas incorporates engineered components or a composite internal structure designed for durability during interstellar transit. Although the data remains incomplete, the presence of non-natural materials significantly strengthens the argument for artificial origin. At the same time, gravitational anomalies began to appear in the object's immediate vicinity. These anomalies were subtle but measurable. Slight perturbations in local space-time curvature, inconsistent with an object of Atlas's estimated mass. Several potential explanations were evaluated. The first measurement error was quickly dismissed after multiple observatories confirmed identical results. The second, irregular mass distribution within the object, could account for some of the deviations, but not for the full pattern observed. The third possibility, the presence of an internal mechanism generating localized gravitational effects, cannot yet be verified, but remains under active investigation. If Atlas possesses such a mechanism, it could indicate advanced propulsion, mass manipulation, or shielding technologies. Any one of these capabilities would place the object's engineering many orders of magnitude beyond human capacity. Analysts note that if the gravitational irregularities are intentional outputs rather than a byproduct of internal processes, the object may be stabilizing its trajectory with precision that cannot be achieved through conventional thrust alone. Meanwhile, electromagnetic monitoring stations reported intermittent bursts of low-frequency radiation emanating from the object. These bursts were faint, consistent, and repeated at irregular intervals. Their structure does not resemble communication signals, but they also do not match background cosmic noise. One hypothesis suggests they may represent internal diagnostics or structural realignments. Another proposes they could be responses to external stimuli, possibly the solar wind or the gravitational fields of nearby planetary bodies. At present, the purpose remains unknown. As these layers of complexity accumulated, scientists issued updated risk evaluations to strategic councils. These evaluations emphasize that while there is no evidence of imminent danger, the object's capabilities continue to surpass expectations. The primary concern is the unpredictability of a system operated by an unknown intelligence or automated directive. If Atlas follows a predefined mission, understanding the parameters of that mission becomes crucial. If it operates autonomously with adaptive behavior, the difficulty increases significantly. In parallel, analysts studied the historical context of interstellar objects visiting the solar system. Previous anomalies, such as the 2017 object Oumuamua, displayed characteristics that raised questions but lacked the definitive behavior observed in Atlas. Unlike its predecessors, Atlas did not simply pass through. It altered its path in a controlled, high-energy maneuver. This distinction makes it the first object to demonstrate operational capability rather than passive movement. Given this, global agencies intensified discussions on potential next steps. One proposal involves launching a reconnaissance probe on an accelerated trajectory to intercept the object. The mission would rely on advanced navigation algorithms to approach Atlas safely and gather direct imaging data. However, the feasibility remains uncertain due to time constraints and the potential for Atlas to alter its course again. A second proposal suggests deploying multiple small probes rather than a single large mission, increasing the chances of successful observation even if the object executes another maneuver. Despite these efforts, operational challenges persist. The energy required for rapid intercept missions is extreme, and the margin for error is slim. Additionally, any direct approach introduces unknown risks. Without understanding the object's sensor systems, if any exist, it is difficult to determine whether approaching Atlas would trigger a reaction. Analysts agree that a cautious strategy is essential to avoid presenting a signal that could be misinterpreted. Simultaneously, debate continues regarding the appropriate level of public disclosure. Agencies recognize that withholding information indefinitely is not viable. If Atlas performs another maneuver, or if its approach distance falls below a defined threshold, the event will become visible to amateur astronomers and independent observatories. At that point, global transparency will be unavoidable. Until then, the priority remains gathering as much verified data as possible before issuing any statements that could cause misunderstanding or panic. Throughout all these developments, one central question persists. What is Atlas preparing to do next? Its current trajectory places it on a path toward a close approach, but not a collision. This suggests intentional positioning rather than accidental convergence. If the object is following a planned route, the next maneuver, if one occurs, may reveal its operational goals. Whether it intends to enter orbit, adjust speed, deploy instruments, or simply pass by remains impossible to determine without further observation. The coming days will be critical. As Atlas continues its steady approach, every minor change in velocity, orientation, or emission pattern will be analyzed for signs of deliberate action. If the object performs a second major maneuver, the implications will be profound. A deceleration would suggest preparation for long-term proximity. A change in orientation could indicate scanning or observation. An acceleration could imply repositioning or continuation to another destination. Regardless of the outcome, the trajectory change has already placed humanity in a position unlike any it has faced before. A potential artificial object is approaching Earth with capabilities that exceed current understanding, and the world must now prepare for possibilities that extend far beyond conventional scientific frameworks. As Atlas advanced deeper into the inner solar system, the task facing global governments shifted from observation to strategic preparation. The maneuver it executed had already nullified long-standing assumptions about cosmic threats and exposed a profound vulnerability within every nation's defense framework. For decades, planetary protection strategies focused exclusively on natural hazards, asteroids, comets, and debris predictable enough to model and intercept. But none of those strategies accounted for an object capable of altering its own course with precision or demonstrating control systems beyond human reach. Within hours of the updated trajectory forecasts, classified high-level meetings were convened across multiple nations. Defense ministers, scientific advisors, aerospace engineers, and intelligence officials examined the same conclusion. No existing technology can stop, intercept, or meaningfully influence an object exhibiting Atlas's capabilities. Even the most advanced weaponry humanity possesses, nuclear-tipped interceptors, directed energy prototypes, or kinetic deflection systems, was designed for targets with no ability to respond. Against an object that can maneuver, accelerate, or adapt, none of these approaches offer a viable solution. This realization forced strategic planners to consider entirely new categories of response. The first category focused on observation to maximum depth. Agencies began pooling resources to create a unified sensor grid capable of tracking even the smallest change in Atlas's motion. Satellites were retasked, radio telescopes retuned, and deep space monitoring assets allocated exclusively to continuous measurement of the object. The objective was simple: detect the earliest possible indication of another course adjustment, speed change, or electromagnetic emission. The second category reviewed communication strategies. Although Atlas has not issued any transmissions recognizable as an intentional signal, analysts cannot rule out the possibility of passive or encoded messaging embedded in its emissions. Several scientific institutions proposed developing a controlled broadcast protocol to test whether the object responds to structured communication. However, strategic councils opposed such action at this stage. Initiating contact with an unknown intelligence without understanding its intent was deemed an unacceptable risk. For now, all communication remains purely observational. The third category assessed potential threat scenarios. These scenarios were not predictions, but strategic models designed to help governments understand the full spectrum of outcomes. The least concerning scenario assumed Atlas intends only to observe Earth during a close pass. A more complex scenario suggested it may enter orbit or adopt a stationary position relative to Earth. A more severe scenario examined the possibility that its path may bring it within the atmosphere or into controlled descent. The most extreme scenarios, though still considered unlikely, evaluated the theoretical consequences of directed impact or deployment of unknown systems. Each scenario influenced different branches of government. Scientific groups focused on data and understanding. Defense sectors analyzed risks and vulnerabilities. Intelligence communities attempted to construct profiles of potential motivations and behaviors, drawing parallels to known patterns in human exploration, automated systems, or probe-based missions. Despite differing perspectives, all teams recognize the same limitation. Modeling the intentions of a system that surpasses human technology by an unknown margin leaves significant room for error. In the midst of these investigations, another concern emerged. Not all nations possess equal access to the data. While the major spacefaring countries are coordinating at a limited level, several governments have not yet shared their internal findings. Some states may interpret Atlas's approach as an opportunity rather than a threat. The possibility of unilateral action, whether scientific or military, creates additional uncertainty. If one nation attempts contact or response without coordination, it risks altering the object's behavior in ways others cannot anticipate. Intelligence assessments indicate that certain governments are already preparing independent missions, potentially aimed at reconnaissance or early communication. These efforts remain speculative, but if confirmed, they introduce significant risk. Any action taken without global consensus could trigger unpredictable outcomes, especially if Atlas possesses autonomous defensive capabilities or interprets the approach as interference. At the same time, global economic and political systems are beginning to feel early pressure. Markets sensitive to aerospace and defense have entered volatile fluctuations due to rumors of classified developments. Diplomatic channels are experiencing increased activity, though many conversations remain undisclosed. While the general public remains unaware of the object's true nature, the institutions responsible for global stability are adjusting to the possibility that humanity may soon encounter a force that does not fit within existing geopolitical frameworks. In scientific circles, the primary question has shifted from what is Atlas to what is Atlas preparing to do? Analysts monitoring thermal output, rotational variance, and localized emissions note that the object's internal systems remain active at a low level. These signatures are neither diminishing nor escalating, suggesting a state of standby operation. This observation has raised speculation that Atlas may be following a predefined sequence navigational, observational, or mission-driven. If true, the upcoming stages of its approach may reveal the next phase of its operational protocol. Efforts to predict the object's potential behavior are underway. Models studying trajectories of autonomous probes propose that Atlas may maintain a close pass distance long enough to gather detailed data on Earth's surface, biosphere, or technological activity. Other models suggest it could position itself gravitationally between Earth and the Sun, a location advantageous for long-term observation. Some even explore the possibility that Atlas may execute a controlled deceleration to integrate into Earth's orbital systems. However, without direct evidence, these remain theoretical frameworks. What is certain is that Atlas's current velocity and trajectory offer several windows during which additional maneuvers could occur. Analysts have identified critical points where adjustments are most likely if the object intends to enter orbit or reduce its speed. Monitoring will intensify as these windows approach. Despite the overwhelming uncertainty, one point of agreement unites the global scientific community. Atlas's maneuver was not an isolated event. It marked the beginning of a sequence, and sequences by definition continue. Humanity now waits for the next action, whether another course correction, a change in speed, a shift in orientation, or a new emission pattern. Whatever occurs next will provide crucial insight into the object's purpose. Until then, governments and researchers remain on alert, aware that preparation must advance even without knowing what they are preparing for. Atlas continues forward, silent and controlled, closing the distance toward a world not yet aware of its presence. The next stage of analysis and the next maneuver it might perform will determine the nature of humanity's first true encounter with an intelligence beyond its own. As Atlas continued its controlled approach, intelligence agencies around the world intensified their efforts to determine the object's possible motives. The maneuver it executed had already ruled out natural explanations, and the absence of further deviations suggested that its current trajectory is intentional and stable. This combination purposeful movement without additional correction prompted analysts to focus on deeper patterns, attempting to understand not only what Atlas is doing, but why it is doing it. The first hypothesis centers on reconnaissance. Under this model, Atlas may be a long-range probe designed to gather detailed information about planetary systems it encounters. The precision of its maneuver could indicate an automated decision-making process triggered once specific thresholds were met, such as detection of electromagnetic emissions from Earth or recognition of industrial activity on the planet's surface. If this hypothesis is correct, the object's approach may be part of a standard protocol executed when a technologically active civilization is identified. A second hypothesis suggests targeted observation. Rather than surveying the entire solar system, Atlas's maneuver could represent a specific focus on Earth itself. Analysts supporting this model highlight the timing of the course correction. It occurred when Earth's position along its orbit allowed for a direct approach vector with minimal energy expenditure. If Atlas's systems are optimized for efficiency, the chosen trajectory could reflect strategic planning rather than incidental alignment. A third hypothesis explores the possibility that Atlas is following a predetermined mission unrelated to humanity. In this scenario, the object's path toward Earth is not driven by interest in the planet, but by a broader navigational requirement. Earth may represent a waypoint, a gravitational assist point, or a location relevant to its larger objectives. However, this hypothesis is increasingly challenged by the precision of Atlas's maneuver. The correction it performed was too controlled, too direct, and achieved with too much energy to be a simple alignment adjustment. A fourth hypothesis considers the possibility of contact, whether observational, passive, or active. Analysts remain cautious with this model due to its implications. If Atlas's maneuver indicates intent to establish proximity to a populated planet, understanding the nature of that intent becomes critical. However, there is currently no evidence of communicative outreach, and no recognizable signals have been directed toward Earth since the maneuver. The object remains silent, producing only emissions consistent with internal activity or propulsion residuals. To evaluate these hypotheses, analysts studied the object's behavior in the context of autonomous systems. Modern human probes, such as those sent to the outer planets, employ decision trees, adaptive navigation algorithms, and fault-tolerant systems. Extrapolating from these principles, an object like Atlas, if artificial, may possess far more advanced adaptations, enabling it to evaluate its environment and adjust its course accordingly. Under this framework, the maneuver could represent a programmed response to specific environmental triggers detected within the solar system. Parallel efforts examine the object's approach vector relative to Earth's rotation and orbital plane. The trajectory it follows aligns with several key observation windows that would allow clear data gathering on Earth's surface, atmospheric composition, and electromagnetic activity. If ATLAS is configured to collect detailed readings, this trajectory is optimal. The stability of its movement also supports the idea that it is not relying on passive drift, but on continuous calculation and real-time navigation. Another line of analysis considers the possibility that ATLAS may contain multiple operational modes. The maneuver it executed may represent only the initial stage of its approach sequence. Future stages could involve deceleration, rotation, orientation adjustments, or deployment of secondary systems. Although speculative, this framework is consistent with the behavior of complex autonomous craft, which often conduct operations in phases based on environmental conditions. This uncertainty has placed additional pressure on observation teams. Every available instrument capable of monitoring ATLAS is now operating near continuously. Agencies are working to identify any signs that the object is preparing for another maneuver. Energy spikes, changes in rotation, shifts in thermal distribution, or fluctuations in electromagnetic emissions could indicate imminent activity. For now, none have been detected, suggesting that the object may be conserving energy or waiting to reach a predefined distance before initiating its next phase. Meanwhile, strategic planners must consider the full range of possibilities that could follow. If ATLAS decelerates within a specific distance, it may be preparing to enter an orbital configuration. If it rotates to align specific structures toward Earth, it may be preparing for targeted observation or communication. If it deploys smaller bodies or instruments, it may be conducting detailed analysis or probes. All of these scenarios carry significant implications, each requiring different forms of preparation. Efforts to model potential outcomes remain limited by the lack of direct information. Analysts do not know whether ATLAS contains biological organisms, artificial intelligence, or fully autonomous systems. They do not know whether it is a singular craft or part of a larger network. They do not know whether it is operating on contemporary input or pre-programmed directives issued long before it entered the solar system. These unknowns shape every discussion and influence every strategic recommendation. Despite the uncertainty, one observation has become increasingly clear. The object's behavior is controlled, consistent, and devoid of error. Its navigation does not display drift, oscillation, or correction loops common in human-made spacecraft. Whatever system governs ATLAS's movements, it operates with precision that suggests stability over extremely long durations. This supports the theory that ATLAS was engineered for interstellar travel and built to function over timeframes far beyond the limits of human-machine longevity. As this understanding deepens, a new question has emerged across scientific panels. Why now? If ATLAS is executing a programmed mission, what parameter triggered its maneuver at this exact moment in history? Earth's technological emissions, atmospheric signatures, and thermal output have been detectable for decades. The timing of the correction indicates that the object either only recently acquired sufficient data to justify the maneuver or that its mission timeline required this specific approach window. This question will remain unresolved until Atlas reveals additional behavior. For now, nations continue to prepare, aware that the next action from the object, whether a second maneuver, a deceleration, or a new emission, will be critical in determining its purpose. Atlas is moving closer. The world remains unaware, and the agencies responsible for humanity's safety are confronted with a scenario for which no protocols exist. As Atlas continued its steady progression through the inner solar system, global committees began constructing detailed scenario models outlining the possible developments that could unfold once the object reached critical proximity to Earth. These models were not predictions. They were frameworks designed to prepare nations for outcomes that range from routine observation to profound systemic disruption. The first category included scenarios involving minimal interaction. In these models, Atlas would perform no additional maneuvers, maintain its current velocity, and pass Earth at a distance close enough for high-resolution observation, but far enough to avoid direct engagement. Under this outcome, governments would focus on data collection, continued trajectory analysis, and preparation for potential long-term monitoring. Although this is considered the least disruptive scenario, it still represents the closest approach of a maneuver-capable interstellar object in recorded history, carrying implications for astronomy, physics, and global policy. The second category explored more active possibilities. Should Atlas execute a deceleration burn within a predetermined distance, analysts believe this would strongly indicate an intent to remain within the Earth-Moon system. A deceleration would require substantial energy expenditure and would signify that the object is not simply transiting the solar system, but preparing for insertion into a stable orbital configuration. Several orbital models were simulated based on its current momentum. Some place Atlas in a high geocentric orbit. Others suggest it could anchor itself at a Lagrange point. Both positions would allow continuous observation of Earth. A third category involves scenarios in which Atlas deploys smaller units or devices. These could consist of probes, drones, sensor platforms, or unknown instruments. Human space agencies routinely deploy secondary modules from spacecraft to increase observational capacity. If Atlas were designed with similar operational principles, deployment sequences may occur once it reaches optimal range. Analysts warn that such deployments could be misinterpreted as aggressive behavior if not thoroughly understood. As a result, contingency planning emphasizes the importance of differentiating between scientific investigation and hostile activity. A fourth category considered orientation changes. If specific structures on the object rotate toward Earth, such as arrays, apertures, or emitter lines, this could suggest targeted scanning or communication alignment. Several monitoring stations have already constructed algorithms to detect even minor rotational variances. Should Atlas reorient itself in a direction inconsistent with inertial drift, the implications will be significant and will require immediate reassessment of its operational intent. A more concerning category evaluated scenarios in which the object performs a direct atmospheric entry or a controlled descent. Although considered unlikely due to the high risk such a maneuver would pose to its integrity, analysts maintain that the possibility cannot be dismissed. Controlled descent models simulate several potential endpoints: high atmosphere deceleration, low Earth orbit insertion, or direct contact with the surface. Each of these would trigger emergency protocols and force governments to initiate immediate public disclosure. Across all scenarios, one problem remained constant: the absence of a unified global response. Nations have begun forming crisis committees, but divergences in strategic priorities are already evident. Some countries advocate for cautious scientific engagement. Others prioritize military readiness. A smaller number consider early communication attempts. This fragmentation poses significant challenges. Without coherent coordination, humanity's response, whatever form it takes, may be inconsistent, potentially confusing, or even provoking the object. Internal documents reveal that several major powers are also developing classified contingency plans. These plans include strategies for securing advantageous positions in the event of contact. Some nations are attempting to accelerate space-based reconnaissance missions, hoping to gather data independently of international efforts. Others are exploring rapid assembly launch vehicles designed to deploy sensors within Atlas's projected flight corridor. These actions reflect not only preparation, but also competition for technological and political leverage. Intelligence reports suggest that certain governments may already be conducting private analysis of intercepted signals or emissions. If this is true, it introduces further instability. Without transparency in data sharing, interpretations may diverge, leading to conflicting conclusions about the object's intentions. Analysts warn that misinterpretation, whether overly optimistic or excessively defensive, could result in actions that alter the object's behavior. In parallel, global institutions such as the United Nations, the European Space Agency, and the International Astronomical Union have begun drafting preliminary documentation for a unified communication strategy. These efforts aim to create protocols governing what constitutes an acceptable response. However, they face significant challenges. The lack of precedent, combined with the absence of verifiable information about the object's origin or capabilities, makes protocol development largely theoretical. The situation is further complicated by public communication concerns. If Atlas performs another visible maneuver, the event will become impossible to conceal. Amateur astronomers, independent research groups, and civilian tracking networks will likely detect the change first, creating a high risk of misinformation spreading before official channels can respond. Governments are preparing statements, though none have agreed on a timeline for disclosure. Back in the scientific community, monitoring efforts remain focused on identifying early signs of a strategic shift in the object's behavior. Observatories analyze its thermal output for subtle increases that may indicate power generation. Rotational mapping systems look for micro-adjustments that might precede a larger orientation change. Spectral teams examine emissions for patterns that could signify communication initiation. Every dataset, regardless of how minor, is reviewed for actionable insight. Despite this constant scrutiny, Atlas maintains its controlled trajectory without deviation. This consistency has led some analysts to propose that the object may be operating on a long-term directive, with the next maneuver scheduled for a predetermined distance rather than environmental triggers. If that is the case, humanity may not receive early warning before the next significant action. This possibility introduces a new strategic challenge. If Atlas initiates a major maneuver without prior indicators, the window for analysis will shrink dramatically. Governments would be forced to interpret its intent in real time without preparation or consensus. For this reason, crisis committees have emphasized the critical need for continuous data flow, redundancy in monitoring systems, and rapid communication channels between major powers. For now, Atlas continues its approach unchanged. It remains the most advanced object ever recorded entering the inner solar system, exhibiting precision, stability, and silence. Its purpose is still unknown, and until its next maneuver occurs, governments must prepare for multiple outcomes simultaneously. As Atlas moved deeper into its approach corridor, scientific institutions intensified their analysis of the object's technological characteristics. For weeks, the focus remained on trajectory, emissions, and structural anomalies. But as more precise data accumulated, attention shifted to the underlying mechanisms that enable its operations. Understanding these mechanisms, however limited that understanding may be, became essential for predicting the object's next possible actions. Initial evaluations centered on the propulsion event that triggered the course correction. The thermal spike associated with that maneuver displayed energy values far exceeding the limits of chemical propulsion or known natural processes. The duration and stability of the burn suggested a controlled reaction capable of sustaining immense output while maintaining directional precision. Several research teams propose that Atlas may utilize a form of energy generation that produces high-density thrust with minimal waste radiation. Some models indicate compatibility with theoretical concepts involving contained fusion or particle-based propulsion systems, though no confirmed principles exist at present. One notable observation emerged from the spectral readouts during the maneuver. Analysts detected a broad emission pattern consistent with rapid ionization events, but the energy distribution did not match any known plasma signatures. Instead, the pattern resembled controlled field manipulation, potentially indicating that the object employs a method of accelerating particles to extreme velocities with little dispersion. If proven correct, this would align with theoretical propulsion models long considered unachievable with current human engineering. Beyond propulsion, scientific teams examined the object's surface temperature profiles. Atlas exhibits unusually stable thermal regulation. Natural bodies, when exposed to solar radiation, display predictable heating and cooling cycles. Atlas, however, maintains temperatures inconsistent with its position relative to the Sun. Some regions remain stable despite significant changes in illumination. Others exhibit periodic fluctuations with no correlation to external factors. This indicates the presence of internal thermal control systems or active heat redistribution mechanisms designed to protect critical components. Another field of investigation concerns the gravitational anomalies detected in the object's vicinity. Although the variations are minimal, their consistency over time has led several physicists to conclude that Atlas may possess a method of altering local gravitational fields. This capability, if confirmed, would represent a level of engineering sophistication far beyond anything humanity has achieved. Some models speculate that such manipulation could serve as supplemental stabilization for long-distance travel or as part of a complex navigation system capable of fine-tuning trajectory without relying solely on thrust. Concurrently, analysts are studying Atlas's rotational behavior. Unlike natural bodies, whose rotation tends to slow or drift over time due to tidal forces or mass irregularities, Atlas maintains a stable, controlled rotation profile. Minor deviations have been observed, but each one corrected itself within a narrow and consistent time frame. This suggests either active rotational compensation or an internal gyroscopic mechanism capable of maintaining balance over extreme distances. If Atlas is preparing for a maneuver requiring precise orientation, these adjustments may represent pre-positioning for upcoming operational phases. Electromagnetic monitoring has also revealed a recurring set of faint, low-frequency emissions. Although these signals do not exhibit the structure necessary for communication, their repetition indicates they may serve as internal synchronization pulses or diagnostic cycles. The pattern is consistent with functioning machinery rather than passive natural phenomena. If these emissions are tied to internal system checks, their frequency could provide an indirect indicator of operational readiness. Recent data suggests a slight increase in their occurrence as Atlas approaches a specific orbital segment, raising concerns that the object may be preparing for a new mode of operation. Another important area of focus is potential energy reserves. For an object of Atlas's size to perform the observed maneuver, it must possess a significant internal power source. This source must be stable over long durations, resilient to deep space conditions, and capable of generating immense bursts of energy. Analysts propose that Atlas might contain an internal reactor or energy conversion system leveraging principles unknown to current science. Some speculate on zero-point extraction, vacuum energy tapping, or advanced nuclear processes. Although these remain theoretical, the observed behavior demands consideration of energy systems operating at scales previously deemed impossible. These technical evaluations have led some experts to raise concerns about the possibility of self-protective systems. If Atlas carries technology capable of navigating interstellar space, it may also possess defensive subsystems designed to prevent damage or interference. These defenses might operate autonomously, reacting to perceived threats without requiring external control. Such systems could range from passive shielding to active countermeasures. In any scenario, approaching the object, whether with a probe, spacecraft, or signal, carries risks that must be thoroughly assessed before any attempt is made. Meanwhile, behavioral analysts have begun examining subtle patterns in the object's activity. Several small variations in emission levels occurred at consistent intervals. Although not dramatic, these fluctuations do not match natural periodic cycles. Analysts propose they may represent a transition or pre-activation sequence preparing the object for a future maneuver. Others caution against over-interpretation, noting that without a baseline for comparison, distinguishing operational signals from background processes remains challenging. Despite the uncertainties, the scientific consensus is that Atlas's systems are active, controlled, and operating with a degree of sophistication far beyond current human technology. The object's behavior does not display randomness or drift, but stable, predictable operation consistent with a functioning artificial system. Global organizations have noted the implications. If Atlas possesses a propulsion system capable of complex maneuvers, a power source of unknown magnitude, thermal regulation mechanisms, gravitational manipulation capabilities, and potential self-protection systems, then humanity must assume the object is engineered for long-term autonomy and resilience. This suggests a mission profile calibrated for interstellar operation, continuation over extensive timescales, and functionality independent of external support. For now, the object remains in silent approach. Its systems remain active but subdued, and every hour brings it closer to the distance at which another maneuver, should one occur, will become visible. Whether that maneuver involves deceleration, probe deployment, orientation change, or an entirely unknown action is still impossible to determine. But the technical analysis indicates that Atlas is not a passive visitor. It is a functioning construct performing actions consistent with deliberate operation. As Atlas continued its controlled approach, global committees shifted their focus toward contact scenarios, ranging from passive observation to direct interaction. The modeling of these scenarios was no longer theoretical. The trajectory data, energy signatures, and increasing stability of the object's behavior suggested that some form of engagement, whether intentional or unavoidable, could occur during its passage near Earth. The first scenario projected a passive contact event. In this model, Atlas would maintain a consistent course, pass within observational distance, and transmit data-gathering emissions toward Earth without initiating interaction. The measurable consequences of such an event include high-resolution surface scanning, magnetic probing, and atmospheric sampling at ranges that would be detectable by Earth-based instruments. These actions, while not aggressive, would confirm the presence of advanced surveillance capabilities. A second scenario considered an active contact sequence. This possibility involves Atlas emitting a structured communication signal, initiating a directed transmission toward Earth's major communication hubs or deep space arrays. Analysts caution that receiving such a signal could produce measurable consequences in global communication infrastructure. Depending on the frequency, amplitude, and encoding, the transmission could overload sensitive systems, create temporary disruptions, or force emergency shutdowns of satellite networks. A third scenario explored direct deployment. In this model, Atlas releases smaller units designed to enter Earth's orbit or atmosphere. The measurable consequences include potential electromagnetic interference, localized gravitational fluctuations, or atmospheric ionization trails. Analysts emphasize that such deployments, while not necessarily aggressive, would represent the first physical arrival of non-human technology within Earth's immediate environment. A fourth and more concerning scenario examines the potential for defensive action. If Atlas interprets any terrestrial activity, intentional or accidental, as interference, its response could be rapid and technologically overwhelming. The measurable consequences would depend on the nature of the defensive systems, but analysts outline possibilities, including atmospheric disturbances, targeted electromagnetic pulses, or kinetic avoidance maneuvers capable of destabilizing satellites or upper atmosphere aircraft. As these scenarios were evaluated, global markets reacted in measurable and immediate ways. Aerospace and defense industries experienced sharp volatility. Corporations associated with satellite infrastructure, propulsion technology, and advanced materials saw sudden spikes in trading volume as institutions scrambled to acquire leverage in a potentially transformed technological landscape. Meanwhile, private space companies once focused on commercial satellite launches and exploratory missions began redirecting their internal research efforts to analyze Atlas independently. Several companies accelerated their classified programs, attempting to develop rapid response probes or advanced observational platforms capable of obtaining proprietary data. The financial sector interpreted Atlas not only as a scientific event, but as a geopolitical and technological disruptor. Market projection systems began recalibrating long-term forecasts, factoring in scenarios where advanced technology might soon recontextualize entire industries. These shifts, while subtle to the general public, became clear indicators that global systems were preparing for a fundamental change. Parallel to these developments, an unexpected phenomenon emerged: a surge in unauthorized astronomical observations. Amateur astronomers, private research groups, and independent enthusiasts began capturing irregularities in Atlas's reflected light and thermal signature. Several of these groups posted preliminary analyses online before being contacted by regulatory authorities. The rapid spread of unverified data, some accurate, some misleading, triggered internal concern within intelligence agencies. The risk of public exposure increased sharply. Shortly after these observations surfaced, the first significant anomaly was recorded. A deep space monitoring array detected a sudden, brief fluctuation in Atlas's magnetic profile. The spike lasted less than a second but was followed by a measurable decrease in the object's rotation rate, too small for the general public to detect, but unmistakable to analysts. The deceleration was deliberate. The rotation slowed by a controlled margin before stabilizing again at a slightly different orientation. This was not a malfunction. It was the first clear indication that Atlas was preparing for a change in operational mode. The anomaly raised immediate questions. Rotation adjustments of this type often precede propulsion sequences, deployment operations, or orientation alignment for energy discharge. Within hours, committees reviewed the data and concluded that Atlas's controlled rotational shift represented the most significant behavioral change since its original trajectory correction. In the wake of this anomaly, an international crisis of trust began to surface. Several nations accused others of withholding critical data regarding the object's emissions, rotation, and spectral fluctuations. Tensions escalated as intelligence agencies intercepted communications indicating that certain governments were preparing unilateral missions, some for reconnaissance, others for potential defensive readiness. These actions threatened the stability of the fragile cooperation that had existed up until this point. The crisis intensified when leaked documents revealed that one nation had conducted clandestine attempts to broadcast low-frequency signals toward Atlas several days earlier. The transmission was weak and unlikely to have reached the object with significant clarity, but the revelation destabilized diplomatic channels. If multiple parties attempted independent communication, the risk of provoking an unintended response increased dramatically. This fragmentation of global strategy raised another possibility, one that had not been discussed in earlier stages of analysis. Several experts propose that Atlas's current approach may not represent the final phase of its mission, but an intermediate one. In this model, the close pass is intended to allow precise evaluation of Earth's capabilities, technological electromagnetic, gravitational, and infrastructural. A deeper sequence may follow, involving orbital insertion, hierarchical deployment, or initiation of contact protocols designed to operate after preliminary risk assessment. This interpretation is reinforced by the controlled nature of the recent rotational anomaly. If Atlas is preparing to shift into a new mode scanning, alignment, or deceleration, then the close approach may mark only the beginning of a larger operational procedure. As analysts reviewed these possibilities, a growing number of strategic planners introduced a new category into the planetary response catalogue: conflict scenarios. While none of these scenarios imply offensive intent from Atlas, they outline the conditions under which humanity may be forced into a defensive posture. These conditions include autonomous deployments entering Earth's atmosphere, targeted emissions affecting infrastructure, or anomalous gravitational behavior destabilizing orbital systems. Regardless of intent, humanity has now entered a phase where preparation for potential conflict is no longer theoretical. The object's capabilities, precision, and silence represent a level of technological asymmetry that cannot be ignored. And with Atlas's rotational change now confirmed, the world stands at the threshold of the next Phase 1 that may unfold far sooner than anticipated. As the global scientific community intensified its monitoring efforts, a new complication emerged: internal data leaks from several government agencies. These leaks did not reveal complete data sets, but released enough fragmented information to expose inconsistencies between official statements and classified assessments. Documents detailing anomalous emissions, rotational adjustments, and risk models began appearing on encrypted forums and private research platforms. Although the origin of the leaks remains uncertain, their emergence triggered a rapid collapse in informational control. Once these documents circulated, scientific institutions found themselves confronted with public demands for clarification. Independent analysts began reconstructing portions of the classified data, piecing together fragments into coherent patterns. This forced several governments into issuing partial disclosures, officially framed as routine updates, while quietly acknowledging that public containment was no longer possible. The release of these data fragments undermined international cooperation further, as nations accused each other of using leaks to gain diplomatic leverage or to conceal unreported observations. In parallel, major private corporations entered the situation more aggressively. Aerospace companies specializing in satellite networks, observational instrumentation, and propulsion research began seeking access to classified datasets. Their objective was not merely scientific curiosity, but the potential acquisition of technical insight that could lead to substantial commercial or strategic advantage. Several corporations announced accelerated research programs, including attempts to develop rapid-response autonomous probes capable of reaching Atlas's projected path. Private spaceflight enterprises with reusable launch vehicles began lobbying for permission to conduct independent intercept missions. Although governments rejected these proposals, internal reports indicate that some corporations initiated unsanctioned research into propulsion systems that could theoretically reach the object within months, exploiting proprietary technology once considered too experimental for operational use. These initiatives, while unofficial, demonstrate a shift toward competition for technological positioning in the wake of Atlas's approach. Simultaneously, a covert arms race began taking shape beneath the facade of scientific research. Several nations increased activity within their classified aerospace sectors under the justification of observational preparation. However, intercepted communications revealed that some of these programs investigated anti-satellite technologies, electromagnetic shield concepts, and experimental energy redirection systems technologies that could potentially be adapted for defensive applications against unknown threats. While no nation has openly declared such intentions, the surge in classified development suggests an escalating concern about the object's potential capabilities. Against this backdrop, the second anomaly occurred. At SO 3:14 UTC, a deep space sensor array detected an unusual shift in Atlas's thermal distribution. Unlike the initial propulsion event, this fluctuation did not correlate with thrust or rotational adjustment. Instead, several localized hotspots appeared along the object's surface, arranged in a linear sequence. Each hotspot increased in temperature for less than 3 seconds before cooling rapidly. 5 distinct thermal events were recorded, evenly spaced and synchronized. Within minutes, secondary observatories confirmed the pattern. The alignment of the hotspots did not match natural stress points, internal fractures, or sunlight exposure. Their uniform spacing and identical thermal signatures suggested coordinated activation of internal systems. Analysts describe the sequence as warming pulses, though their function remains unknown. Some propose that these pulses may represent system checks, module activations, or calibration procedures. Others note the possibility of energy build-up preceding a larger operation. The most significant aspect was the timing. The anomaly occurred exactly as Atlas crossed a distance threshold predicted in earlier simulations as a potential deceleration point. Although the object did not reduce speed, the alignment between the predicted threshold and the thermal sequence suggests that Atlas may be preparing for a future maneuver. The systematic nature of the pulses indicates an internal transition phase, possibly marking a shift from cruise mode to operational mode. This development caused immediate concern within global response teams. If Atlas is moving into a new phase of activity, the next maneuver may be imminent. Analysts scrambled to determine whether the pulses represent orientation alignment, sensor activation, or structural reconfiguration. Supporting this interpretation, small but consistent changes appeared in the object's magnetic signature following the anomaly. These fluctuations were too subtle for public observation, but significant enough for experts to consider them part of the same operational sequence. Following the second anomaly, the crisis of trust intensified. Nations accused each other of withholding prior knowledge of the predicted threshold or of attempting to intercept the data regarding the pulses. Diplomatic tensions escalated as intelligence agencies demanded immediate data transparency, fearing that any concealed information could jeopardize coordinated response strategies. Meanwhile, additional leaks surfaced, this time from private contractors involved in classified satellite analysis programs. These leaks included partial images suggesting that the thermal pulses formed a geometric pattern when mapped onto the object's surface. Although experts cautioned against drawing definitive conclusions from low-resolution imagery, the geometric alignment fueled speculation that the activation sequence represents a structured system, possibly an array, panel line, or instrumentation rail. The appearance of structured activation across multiple points indicates that Atlas may be using modular systems designed to function in synchronization. If so, the object could be preparing to activate a propulsion module, deploy external components, or initiate a scanning operation aimed toward Earth. This series of events triggered a new wave of public concern. Despite attempts to limit exposure, discussions on independent science networks began circulating theories regarding Atlas's next potential move. Monitoring agencies responded by increasing their operational readiness. High-resolution satellite arrays were retasked, observatories extended their observation schedules, and intelligence sectors began planning for the possibility of a rapid sequence of maneuvers. In strategic circles, the interpretation of the second anomaly marked a turning point. While earlier assessments considered deceleration unlikely, the thermal pulses and magnetic fluctuations reopened the possibility that Atlas may slow in the near term. If this occurs, analysts predict that the object could either adopt an orbital trajectory around Earth or enter a stationary position relative to the planet. Both scenarios carry substantial implications for global security. More concerning is a theory now gaining attention that the close approach may not represent the final phase of Atlas's encounter with Earth, but an intermediate stage. Analysts propose that Atlas could be conducting preliminary system checks required before a major operation, such as deployment of smaller constructs, activation of observation arrays, or initiation of communication protocols. If true, the object may not simply be approaching Earth, it may be preparing for extended presence within the planetary system. For the first time, conflict scenarios are no longer theoretical abstractions. The activation of internal systems suggests that Atlas possesses capabilities far beyond passive observation. If these systems include defensive or operational components, any misinterpretation or unauthorized engagement from Earth could trigger a reaction with unpredictable consequences. The second anomaly marks the beginning of heightened uncertainty, the next detectable change. Whether a deceleration, an orientation shift, or a new emission will determine how the global response must evolve. Atlas is entering a new operational phase, and Earth is moving closer to the moment when observation will no longer be sufficient.